Assalamu alaikum wa rahmatullah. I am Dr. Bilal, Assistant Professor, Department of Chemistry, Kuwait University of Science and Technology. Welcome to online course Physical Chemistry, Chem 332. In today's lecture, we will discuss effect of temperature on reaction rate. So, in this lecture, we will cover effect of temperature on reaction rate, what is the Arrhenius equation, and then how we determine activation energy using Arrhenius equation. So we know the rate of the reaction, which is the change in the concentration of reactant or product. This depends upon the different parameter. First one is the concentration of the reactant. So it depends upon the order of the reaction. If the reaction is first order, second order or third order, the rate of the reaction will be increased with increase the concentration of the reactant, and also the rate of the reaction will be decreased with the decrease of concentration of the reactant. As we know here, with increase the concentration, the rate of the reaction will be increasing. Similarly, the rate of the reaction is affected by temperature. Increasing the temperature of the reaction, the rate of the reaction will be increasing, and decreasing the temperature, it decrease the rate of the reaction. Also, the rate of the reaction is affected by activation energy. Lower the activation energy, higher will be the rate of the reaction, and higher the activation energy value, lower will be the reaction rate. The next one is the catalyst. So catalyst actually decrease the activation energy. So by adding the catalyst to the reaction, increase the rate of the reaction. So we discuss that temperature affect the reaction rate. Now this we will explain by two ways: directly how is experimental result give, and one by the Arrhenius equation. So as we know, the temperature is the average kinetic energy of molecule, and average kinetic energy is equal to 1/2 mv². So higher the velocity of molecule, higher will be the temperature of the molecule. So increasing the temperature means we increase the velocity of molecule, and velocity of molecule is increasing, the collision between the molecule will be increasing, and most molecule will be greater energy than the activation, so they will easily convert into the product, and the rate of the reaction will be increasing. As we know that there is a billion collision taken place between molecule per second. Now each collision is not fruitful. There is some fraction of collision will able to convert the reactant into the product side. Here we discuss that temperature what will be the distribution of energy of molecule at different temperature. As we know, this is the lower temperature, this is the higher temperature energy distribution of molecule profile. So at lower temperature, here fraction of molecule is the lowest energy, and this molecule is the most of the molecule have that type of energy at that temperature, and fraction will be that much energy molecule will be present in the system. So this maximum distribution, this peak represent that the most of molecule have this energy at that temperature. And now when we increase the temperature, actually we shift this peak toward the higher energy side. Now if the activation energy, this is the activation energy barrier, so at lower temperature the small fraction of molecule will have a sufficient energy to cross the activation energy barrier, while at higher temperature a large fraction of molecule have sufficient energy to cross this barrier. So rate of the reaction will be increased, because large number of molecules have sufficient energy to cross the activation energy barrier. Here in this graph we represent how with the increase of temperature the maximum distribution of energy of molecule are shifted. So lower temperature, no molecule, the energy activation energy barrier, so no reaction will be taken place. If you go to the 600, so small fraction of molecule will cross the energy barrier and the reaction will be start, mean reactant convert into the product. If we increase the temperature to 1000, this fraction will be increased to that point. So large fraction of molecule will have greater energy and the rate of the reaction will be increased. Now it was experimentally found that that the rate constant is nearly double for reaction with the rise in temperature by 10 degrees. So if we plot temperature versus the reaction rate of the reaction, it is exponentially increased. Now next incoming slide we will discuss what is the Arrhenius equation. As we know, when the reaction proceed, the reactant go or follow this route, they pass through this barrier to convert into the product side. Now this, when the reactant cross this barrier toward the product side, these two type of product is formed. In one type the product have a higher energy than the reactant, and such type of reaction the energy will be absorbed, delta H will be positive, so the reaction will be endothermic. If the product have lower energy than the reactant, now the change in enthalpy will be negative and the reaction will be exothermic. However, I should mention here that for both exothermic reaction and endothermic reaction, the barrier is same. They should cross this barrier before going to the product side. Only the endothermic and exothermic is telling us whether the product have lower energy or higher energy than the reactant. This is the Arrhenius equation, which was first of all proposed by Dutch chemist J.H. van 't Hoff, but Swedish chemist Arrhenius provided the physical justification and interpretation to this equation. This equation Arrhenius derived or formulated this equation using the collision theory of molecule. So here this represents the rate constant, P is the orientation of the molecule, Z is the collision of molecule, and E is the activation energy, R is the gas constant, T is the absolute temperature. Now what is the postulate of Arrhenius equation? First postulate is the molecule should have minimum energy to form a product during a collision between a reactant, and this minimum energy we will call activation energy. Increasing the temperature of reaction generally speed up the process, increase the rate because the rate constant is increasing. Also, if activation energy is much higher than the kinetic energy of the molecule, the reaction will occur slowly. If the molecule kinetic energy is lower than the activation energy, the reaction will proceed slowly. However, if the activation energy is smaller than the average kinetic energy, the reaction will occur rapidly. Here we represent how the activation complex is formed when A and B react with each other. There is transition state in the reaction path. So this transition state need energy, which we will call activation energy. So the difference between the product and the reactant energies we will call delta E, and this will give either the reaction is exothermic or endothermic, while the difference between the energy of transition state and the reactant we will call activation energy. Now in this slide we represent, here we in Arrhenius equation, this one, this PZ, in some book this PZ we represent by A. This A is the Arrhenius equation constant, which depend upon two parameters: the frequency, collision frequency, and the orientation of the molecule. Collision, as we know, if we increase the velocity of molecule, the collision will be increased, and the molecule, if a sufficient energy, then they will convert into the product. And another is the orientation of the molecule, which we will discuss in this slide. So if molecule have sufficient energy, means greater energy than the activation energy, and there is collision taken place between the molecule. However, the collision is not properly oriented. They are not. The reactant is not properly oriented. The product will be not formed. They will bounce back toward the reactant side. So, for reaction to proceed to product side, the orientation of the molecule is necessary, and the orientation is represented by P in the Arrhenius equation. Now, how we determine the activation energy? There is two-way, graphical and experimental. If we graphically have determined, we have Arrhenius equation. So if you take the natural log of this equation, this will be ln k is equal to ln a plus ln e raised to power EART. Now, if we this is the straight line equation. Ln a represent the intercept, 1 over t represent the x component, minus e over r is the slope, ln k is the y component. So if we plot a graph of natural log of rate constant versus inverse temperature, they will give the straight line. And this is decreasing because minus the slope is minus EA over R. Now if we rearrange the equation, this will give a activation energy equation. So if the rate, as we know, that when increasing the temperature from T1 to T2, the rate constant is changing. The rate constant is changed with increase of temperature. However, one of the parameters that has not changed is the activation energy. Activation energy is the slope. Slope will be same, only the rate constant of the reaction will change with temperature, and then from that slope we determine the rate of the reaction. Next is if we determine the rate constant at two different temperature, we can arrange two activation energy equation at two different temperature. We will subtract equation number 2 from 1, we get this equation. Now if we rearrange the equation will become ln k2 minus ln k1 is equal to minus EA over R into 1 over T2 minus 1 over T1. Now this minus EA over R will give the activation energy, and we determine if we know the rate constant at two different temperature. Thank you very much, and next lecture we will discuss collision theory.